That one was not too bad? Huh, interesting. I'm not saying it has to be too bad. I'm just, skeptical.
You just have to know which properties to try. You've got a lot of properties to work with, and if you don't work with the right ones, it gets nasty.
Yeah, I think that's fair. So I'll begin with a prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Help us to glorify you when we do, Lord. In your name I pray, Lord Jesus. Amen. So my hint that I probably should have made a homework problem and I just neglected to do it. It's just this. If you have W is a subspace of V and the dimension of V is, equal to n, which is less than infinity, then the dimension of the annihilator of W is equal to the dimension of V minus the dimension of W. But it's a little bit more than that. In particular, if we let beta sub W equal to, say, F1, Fk, basis for W, and extend to beta a basis for V, then the usual notation beta dual given by F upper I, F lower J is Kronecker delta Ij gives the annihilator of W is actually the span of Fk plus 1 Fn. So it's not just that the dimension is complementary in that sense, it's also that I can actually straight up build the basis for the annihilator by looking at the dual vectors which are outside the direct duals of the subspaces vectors, whatever you want to call that, I don't know. I would say state this as a lemma, prove this, and then use this to do about the last three homework. Any homework problem which involves annihilators and subspaces, this is going to be super helpful for. I have a solution, and then I look at it, and I tilt my head and squint and go, oh, wait a minute, if I knew this, then my solution kind of like collapses down, blum, 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 and it's easier. So that's my hint. I'm not saying that you should just assert these things to be true. I'm saying that you should try to prove that what I'm saying to you here is true, It's not hard to prove, but you should check it out. All right, so now that we've got that, let me move on here. And I did find the last problem from the book I found to be challenging. I think that was a pretty challenging homework problem. One of the directions was easier than the other. I think you oftentimes find that with these if and only if kind of problem, right? But okay, so anyway, here we go. So introduction to algebra. What do I mean by that? You're like, I already know algebra. What are you talking about? Well, fair enough. So here's the definition. An algebra is a vector space, which I'm going to call A, over a field F with a multiplication. What's a multiplication? So we're going to use the symbol star for that. That itself is going to be a mapping from the Cartesian product of the algebra in itself back to the algebra. All right? And we're going to assume that this multiplication satisfies some basic conditions, like it's going to have to be for example, if we have cx plus y, and we're multiplying that by z, or if we have, x times cy plus z, and we're multiplying that, well, we got c times x times z here, and then plus y times z. And over here I've got c x times y plus x times z. All right, and this would be for all x, y, z in the algebra and c in the field. So collectively, these two properties have a name. If you put them together, you could say this is the bilinearity of star. All right. So that's the starting thing, is I want my algebra to satisfy these bilinearity properties, right? In particular, it just reduces to plain old garden variety scalar multiplication, right? In some sense, like you can pull scalars out, right? But there's more. We say A is associative if you have x, goodness gracious, x times y times z makes sense. So I can either multiply x, y first, and then z, or I can multiply y, z first, and then x, like that. It's associative, if that's the case. And it's unital. Unital if there exists one, I'll say 1 sub a in the algebra, such that 1 sub a times x is equal to x times 1a on the other side for all x and a. So unital just means that there's some algebra element which behaves like the number 1 does for multiplication. All right? And then, so that's it really for us, for the sort of abstract perspective. This is what an algebra is. An associative algebra over a field is simply a multiplication that's bilinear and has associativity. And usually I want to think about it being unital. So there's some number 1. You can also talk about a commutative algebra. What do you think it would mean if the algebra is commutative? The multiplication is commutative, right? So commutative would mean that x times y is equal to y times x for all x and y in A. That would be a commutative algebra. Many of the most interesting examples are commutative algebras. But that's it. This is pretty plain, almost featureless concept of algebra. Like, can you guys give me any examples of algebras? While you're thinking, I'll make a remark. We usually drop the star and simply use juxtaposition, which means, like, we think about x, y under the multiplication mapping to x times y. So a lot of times we'll just write x, y for that. All right. So example 1, what if we just let a equal to the real numbers and use the regular multiplication? Is that an algebra? Is the real numbers a vector space? Mm-hmm. It is. Does multiplication satisfy these properties? Certainly does, right? So it's an algebra. Example 2.
Would all fields be algebras?
A equals to a field is an algebra. Yeah. Over F, yeah. Fair enough. But perhaps a more interesting example would be complex numbers over the real field. That's actually kind of an interesting algebra because the rule for it is non-trivial. So if I take, x plus iy times a plus ib, well, what's the rule? Well, it's, xa minus yb plus I times, xb plus ya. That, for all intents and purposes, is a definition of complex multiplication. Well, complex multiplication is bilinear and it's associative, and in fact, it's commutative, right? So for any algebra, you can look at, there's not many things to think about for an algebra, but one of the obvious things to think about for an algebra is we could think about like the units of the algebra, meaning like, x in A such that there exists x inverse in A, and x times x inverse is equal to the identity, right? If you don't mind, I'm going to use juxtaposition now because writing star every time for the operation is kind of a drag. You'll forgive me. So the set of, and I mean, I guess technically I should do both sides here. I don't want to, I mean, if it was a commutative, it wouldn't matter to assume both sides or not, So this would be the units, so-called units of the algebra. In other words, they're the algebra elements which have multiplicative inverses, right? On the other hand, you could also talk about the zero divisors of A, which would be like x in A such that there exists y not equal to 0 with xy equal to 0, right? I guess probably yx. I don't know if to be careful, I probably should, for the sake of non-commutative algebras, develop a more careful notion of like left and right zero divisors. But listen, we've only got about 40 minutes to talk about this, so I'm going to try to make the most of it. All right. So my goal in the next half hour or so is to get you to understand what an algebra is, what the concept of an algebra is, and how matrices that you already know and love reveal many things about algebras. So for the complex numbers, what are the units? What are the zero divisors? Which complex number do we have a multiplicative inverse for? If you're taking complex right now, you should know that 1 over z we can calculate by z bar over z bar, which is just like x minus iy over x squared plus y squared. That's equal to x plus iy inverse for x plus iy not equal to 0. So that's it. That's the story for complex numbers. Every non-zero complex number has a multiplicative inverse, which is simply given by this formula you might have learned in high school. Multiply by the conjugate. That denominator is non-zero, provided that, as long as either x or y is non-zero, this is certainly non-zero, right? There's no problem with that formula. But then the question is, for other algebras, how does this go? Like, let's look at another example. Example 4, we could look at the direct product algebra. R cross R, the direct product algebra. And here's how that works. If we have x1, x2, and we multiply it by y1, y2, that's simply x1, y1, x2, y2. I think in my notes I point out that this can just as well be done in n dimensions. You can talk about the direct product algebra for Rn. And this is kind of a stupid and, well, it's not stupid, but it's just a natural, silly algebra to think about. I have many Calculus 3 students who believe in this algebra whenever they calculate dot products, because they give me the dot product as a vector, but they're actually calculating this product, right? So, yeah. Not a good place to be in Calc 3 if you write that down. But anyway, my favorite moment in Physics 1 last semester was I had one student call another student a fool because he wrote the dot product as a vector. Like literally in class, or like before class, he's like, "You fool! You've written the dot product as a vector." I was like, "Oh man, student, that student, I could kiss him." What? Yeah.
Is that called the direct product?
Yeah, the direct product of R and R. This is the direct product algebra. So then you can ask the question, what's the identity? Like, what's the multiplicative identity in here? So it turns out, if you look at 1, 1 times, say, x1, x2, it's equal to x1, x2, right? So the 1 of the algebra is actually the pair 1, 1 in this context. And how about, what's the inverse? It's fairly obvious, right? If I've got x and y like that, and I multiply it by 1 over x and 1 over y, I get 1, 1, right? So this, you can see from this that xy inverse is equal to 1 over x, 1 over y for what? X comma y in R with x not equal to 0 and y not equal to 0, right? So if I was to draw a picture here, and I could, here's my x1, here's my x2, those two axes I just drew are a picture of the zero divisors of the algebra. Because those are the places where either the x coordinate or the y coordinate's 0. And those are the places where I can't invert the pair with respect to the direct product algebra. Everywhere else in the 4 quadrants, I have a multiplicative inverse. I've got one here and here and here and here. Great. And the inverse is rather kind of silly, isn't it? Yeah. Another example. Aw, man. Another example is what I like to call the hyperbolic numbers. And so these are things of the form x plus jy, such that x and y are real numbers, and j squared is equal to 1. In other words, the hyperbolic numbers have a multiplication defined as such. X plus jy times a plus jb is xa plus yb plus j times xb plus ya. That defines the hyperbolic number multiplication. So, in other words, h is R2 with E1 as 1 and E2 as j. That's the notation, right? Like basically your x plus jy is really another notation for x comma y, where you're encoding the multiplication by just saying that E2 times itself is equal to E1, essentially, is the rule here. This is a commutative algebra. All right? What are its zero divisors? Well, let me show you what they are. If we take 1 plus j and we multiply it by 1 minus j, we get 1 minus j plus j minus j squared, which is what? 1 minus 1? A 0. This is 0, but these guys aren't 0. These are 0 divisors. And you can take any multiple of those. So if I draw a picture of the hyperbolic numbers, like so, the 0 divisors actually turn out being the locus of the points along the lines y equals x and y equals minus x. These are the 0 divisors of h. Now, I haven't proved that yet. Everything that doesn't fall on those two lines actually has a multiplicative inverse. And guess what? It's given by striking similarity to the complex number system. So like z inverse, you can actually do x minus jy over x squared minus y squared, as it turns out. That's the formula for the multiplicative inverse. Notice that that makes sense as long as we don't have y equal to plus or minus x. Now I'm just dropping these facts on you like they're just, I don't know where they came from, right? I just happen to know these things. But you might ask a question, is there any kind of like systematic method for deriving, for example, the 0 divisors and the formula for the inverse for a given algebra? If I give you the multiplication rule for an algebra, can we derive the set of 0 divisors and the formula for the inverse? Is there some kind of systematic method for doing that? Well, if I'm asking the question, the answer's got to be yes, right? So otherwise it'd be kind of a stupid question to ask, wouldn't it? I guess I could ask the question and then they'd be like, I don't know, that's why I gave you guys homework. Go figure it out for me, you know? That's why I have students. But I try not to ask too many open-ended questions in the homework. I'm not saying I wouldn't. Just saying I don't try not to do that as a default. So, interesting concepts here. One of the main interesting concepts is the question of isomorphism. So, definition. A and B algebras over F are isomorphic. And let me say that this one comes with star and this one comes with, I'll call it box for its multiplication. All right? If we can find psi as a mapping from A to B, such that psi of, let's say, V times W is equal to psi of V box psi of W for all V and W in A. And psi is a linear bijection of A and B. I'm not, so guys, I'm sorry, it's one of those last things on my list of things I'm a little shaky on, but I think part of the definition should also be where psi of the 1 in the A is equal to the 1 in the B. So that's also necessary. We need our algebra isomorphism to map the identity in the one algebra to the identity in the other algebra. So up till now we've talked about isomorphism in this class, isomorphisms of vector spaces, right? Well, now there's more at play. We're talking about an algebra, so there's also a multiplication, right? And so now we can think about transferring the multiplication rule as well. So like an example of this, which is kind of another example of algebra. Another example, example 6 here. We could look at the algebra, which is, say, linear maps from Fn to Fm, right? Under composition. So the multiplication is the composition, right? If we have T and S, in A, then T composed with S is an element of A, right? And you can check that composition of linear maps satisfies that bilinearity rule. If we have a linear combination of T, or we replace S with a linear combination, it does break up just like you'd like. It does have the bit bilinearity property. And what's the identity? What's the one for this algebra? Oh, my bad. My bad. We need to make that n. If it was blowing your mind, that's good. You're thinking. Some of you are more lost, so your mind was not blown. So it's fine for now. But so yes, for mappings from Rn to Rn, well, you again get a mapping for what's the identity here? I mean, what's the unity for this algebra? Is just the identity on Fn. Yeah, that's the one for the algebra, right? Because if I take the identity map and I compose it with another transformation, I just get the transformation back again, right? And the same is true for the opposite composition. Well, this is an algebra. And there's another algebra out there we could call the n by n matrices. So with respect to what's my multiplication here? What should my multiplication on n by n matrices be, do you think? Regular matrix multiplication. Exactamundo. And that's it. That satisfies bilinearity. The identity is simply the identity matrix. It's an algebra. What's the isomorphism? What's the isomorphism of these algebras? The standard matrix of T. We have a winner. You are correct, sir. Very good. So there you go. That is in fact an algebra isomorphism, because we have proved, and you should remember from 221, the standard matrix of the composite is the product of the standard matrices composed. Yeah. That's the isomorphism rule right there. See, because that's here box is just juxtaposition and star is composition. So like the star is equal to the circle and the box equals well, I don't know what to put there, but juxtaposition. In other words, we're not writing it, It's just adjacency indicates the product. We use juxtaposition for the complex number product, for the hyperbolic number product, for the matrix product. We use juxtaposition as a notation for the product in many algebras. All right, well, yes.
Is there a difference between those two classes?
Oh, yeah. The difference is that I forgot to put the hat and the feet on this one. There we go. Thank you. Hey, if it's any consolation, I've been randomly capitalizing or not capitalizing annihilator like the last day or two. I can't make up my mind. Is it lowercase n? Is it uppercase n? The book doesn't even have the n. It's got this upper sub-zero, whatever that's about, All right, so moving on here. So these are some examples of algebras, and I want to show you something quite beautiful. So let's let A, be an algebra of dimension n over f. I can tell you what, I'll let it be R for the sake of specificity. I'm almost always interested in real algebras. I think every problem I've given you in the bonus project is about real algebras. This is all real algebras all the time. Check this out. We can define, let's say A be an element of A, and define L sub A as a mapping from A to A by L sub A of x is equal to A times x. This is called left multiplication by A. You can also define R sub A of x is equal to x times A like that. Remark, LA and also RA are elements of the linear transformations on A itself, right? They are linear transformations from A to A. How do I know that? Well, I'm assuming that the multiplication is bilinear, right? So bilinearity gives me the needed linearity for these maps. Yeah? Like L sub A of Cx plus y is equal to A times Cx plus y, which is Ca times x plus A times y, right? Which is C times La of x plus La of y, right? Therefore, La is a linear transformation as claims. The left multiplication maps are linear transformations. Claim, if we look at the set of L sub A such that A is in the algebra, this is a subspace of the linear transformations on A. What I'm claiming is that it is a subspace in the sense of linear algebra. It's closed under addition. If I take the sum of two such things, right? It's again such a thing. So the sum of two left multiplications maps is again a left multiplication map. In fact, theorem, if I take psi of A equals to L sub A, this is an isomorphism of algebras. So what I'm actually saying here is I can trade my algebra for like the multiplication maps of the algebra, which is kind of like, well, all right. Let's see here. But what's perhaps more interesting is if beta is basis for A over R, then psi of A equal to L sub A of beta is an isomorphism of algebras. Let me actually show you how this works out too. I think in my bonus project I'd given you another name for this. I call it like M of something, or I'm not going to try to recreate the notation in the bonus project right now. But I do want to show you how this actually works in, for example, the case of the hyperbolic numbers. Oh, goodness. Suboptimal. So for instance, if we look at, well, let's look at the complex numbers for a second here. So what's left multiplication by a plus ib if we let it act on x plus iy? How's that work? We've got, a plus ib times x plus iy. That gives us, ax minus by plus I times bx plus ay. And I can rewrite that as a minus b, a times xy. So this right here is actually the isomorphism that I was just talking about in action. I probably should slap a sub beta on this since it has a beta dependence, And if I do that obnoxiously here, this is with respect to the basis being like E1 and E2, which in the usual notation is 1 and I in complex. So this is the matrix representation of a complex number. If I go through the same calculation for the hyperbolic numbers, left multiplication by a plus jb, again, let it act on x plus jy, I get the same formula but with a plus instead of a minus. So if I rewrite that as matrix multiplication, I get A, I get B, I get B, I get A times xy. And when you sort through all the details, this turns out to be exactly the isomorphism I was just talking about in the context of this example, the hyperbolic numbers. All right. So here's the thing, is the let me introduce a slightly easier notation. Instead of psi beta of z, let's just call it m. Excuse me, my bad. I said psi beta of, oh, I had the a there. I'm sorry, I'm supposed to have a plus, you guys should call me on this, a plus ib. I should at least be consistent within this lecture, right? That. So what I'm trying to say is if I have psi beta of some number z, let's call that matrix the matrix of z. And so my point here is simply this. there's a beautiful thing that happens, which is that the matrix of Z inverse has to be the matrix of Z inverse. So this is in the algebra. This is in matrices. This has to be how the isomorphism works. Isomorphism has to map invertible element to an invertible element because it preserves the product. But we know how to check whether or not a matrix is invertible. What do we do? Linearly independent. Well, you're thinking too small. Let's be greedier. We need that the determinant of the matrix of Z is not equal to 0 for the matrix of Z inverse to exist. So to figure out which algebra elements are invertible, I can look at the matrix representation of the algebra and calculate the determinant of an arbitrary element. Wherever that's non-zero, I've got an inverse. And I can write down a formula for it using the classical adjoint formula from linear algebra, which we all remember from Math 221 since it was taught there. Probably. I'm kind of joking. But so how about this? Where is this matrix? Which of these matrices are invertible? What's the determinant of A, B, B, A? Well, it's A squared minus B squared, right? And that would be equal to 0 in the case that B is equal to plus or minus A, right? That's exactly what I was telling you. The zero divisors are where y is equal to plus or minus x. Those are the places where the matrix representatives would have determinant 0. And also, it's more than just this. What's the inverse of the matrix A, B, B, A? It's a 2 by 2 matrix. What's its inverse? Flip the diagonal, kind of boring. Minus is on the off diagonal, less boring. That, my friends, is exactly the matrix of A minus Bj divided by A squared minus B squared. You see, the 2 by 2 inverse formula derives the formula for the inverse of a hyperbolic number if you're willing to use the isomorphism of the hyperbolic numbers to the 2 by 2 matrix algebra. My larger point to you is simply that if you start thinking about algebras, you can derive a vast amount of very interesting results by trading the problem that you're given in terms of some abstract algebraic setting for the much more familiar, warm, cozy world of I can calculate a determinant. Yeah? I think it's kind of neat. Like an example that we spent a fair amount of time thinking about when I started down this path was, by the way, the representation by left multiplication operators is called the regular representation. And this matrix, taking the matrix of the regular representation is usually called the matrix regular representation. Another example that I think is really interesting is, what example am I on? 5, 6, 7, I don't know. 7? Feels like 7. I like this one. I call this H3. These are the 3 hyperbolic numbers. These are things of the form x plus jy plus j squared z, such that j cubed is equal to 1. Now, if I write this in the kind of notation we've been using lately, this is the direct sum of the subspace 1 times r, j times r, and j squared times r. So what I'm saying is that 1j and j squared are linearly independent, and that the whole set of the 3 hyperbolic numbers can be formed in this way. And if you look at the matrix representative of, say, a plus bj plus cj squared, what you get, as it turns out, is this. A, B, C, C, A, B, and C, B, A. So that's what the matrix representative of a 3 hyperbolic number looks like. Now this one's interesting. If you look at this one, it turns out that this character, it's got a zero divisor plane. So if you got like a plus b plus c equals to 0, that fills out this plane. It's a plane of zero divisors. And there's also a line, which is like basically the span. Oh, you guys had in the homework, this thing. So it's the, the line that's the normal line to the plane. That normal line and that plane, they're all zero divisors in the 3 hyperbolic numbers. So, by the way, do you guys have any, if you look at these two problems over here, what do you think about example 4 and example 5? There any similarity here? Daniel, can you? You say, oh, rotate? Right, so the zero divisors are the axes here. The zero divisors are these lines here. It is in fact true that the hyperbolic numbers in the direct product algebra are isomorphic as algebras. In fact, this is just a different notation for that in some sense of algebra. So that was surprising to me when I first learned it. But anyway, so the bonus project, I give you a bunch of questions where you get to explore this concept of algebra and see if you can answer some interesting questions about it. I've shown you some of the basic ingredients. I think I may have half worked one of your homework problems today, maybe a couple of them. But so you might wonder, like, why in the world am I doing all this? Like, well, part of the reason is we give you, like, we have 2 semesters of modern algebra here, abstract algebra, and there are any number of years where we don't ever actually define algebra. See, because modern, like 421 is about the study of groups. Well, a group is a set with an operation which is closed under inversion, and it's an associative. It's an associative operation with an identity that's closed under inversion. This is a group, right? There's no sense of addition, right? There's no vector space, anything going on there, right? And then we talk about rings in Math 421 typically. A ring is essentially a set with 2 operations, and there's an addition and a multiplication, but again, no vector space structure necessarily. All right? So we never quite get around to talking about algebras in abstract algebra, which I think is kind of ironical, to quote Dr. Wang. And this is what an algebra is. It's simply a vector space with a multiplication. And you might ask, well, so how many different examples are there of associative algebras? There are endless examples. This used to be a branch of mathematics. You can find books. For example, there's a book by Pierce from around 1888 where it's just hundreds and hundreds of pages of tabulations of the different kinds of associative algebras which would not be isomorphic. Like just lists and lists and lists of them. But I'm particularly interested in the calculus of these things. Like, how do you do calculus over an associative algebra? That's one of my research interests. That's not really the reason this is here, though. The reason this is here is because I wanted to present you guys determinants from a really different perspective than you saw in 221. And so what I'm going to do next class is I'm going to introduce a different notion of algebra for a vector space called the exterior algebra. So if we're given a vector space V, we can define what's called an exterior wedge product that, so if I take like 2 vectors, x wedge y, this gives me a new object called a 2 vector, if you like. Now, the exterior algebra doesn't make the vector space into an algebra. It makes something bigger than the vector space into an algebra. That's why it's called the exterior algebra, because the vector space is just a tiny part of it. But anyway, I'll explain to you what this is next time, and we'll use it to define the determinant. All right? And So anyway, I hope you'll find that interesting. If you don't, I'm sorry, but I'm trying to make it interesting. So anyway.
That notation looks suspiciously similar to the conjunction.
Conjunction. Oh yeah, we don't believe in conjunction.